So it's important to keep that in mind, and we'll keep updating RAID as more methods come out, and especially with virtualization, we're looking into that and things like that. But this is where we are right now, and the design was for it to be the best at this point in time. And tomorrow or in 4 hours when Joanna presents, it might not be. So it's just important to keep that in mind, that the game, it's always changing, and just, so we have to evolve with it. Things RAID won't do: it won't find hidden processes. It will find hidden processes. It won't find hidden files, registry entries, or directories. This is a feature that's not currently in the works, and there's no plans for it. So that's something that we had to pick and choose what we wanted in the time frame we had, and that was something we left out. RAID does not restore driver, ERP, IDT, and MSR hooks. I am doing some research on the IDT restoring, but the ERPs and MSR stuff is not in the works. It's too dynamic to figure out what the original value was. At the moment, RAID won't identify hidden drivers. That will be added in the next version, for sure. And finally, and this is the difference between a lot of different talks, if the driver is hiding in plain sight, meaning I can run device tree from OSR, or I can run some device tree that dumps the drivers, RAID won't pick it up because it's not hiding. And it's important to keep that in mind. If your rootkit is hiding in plain sight, and by that you mean it's not hiding at all, then you can just look at a device tree and see, hey, that device doesn't look familiar, and look at it from there. So that's something RAID just to keep in mind. All right, so originally I had this really cool thing where RAID is an acronym, so the A was highlighted and the A was highlighted and everything else was grayed, but you won't be able to see that, so just pretend like it's there because I worked hard on that. It took me a good 5 minutes. So RAID's analyzing mode, it will analyze the user mode for user hooks. So if it will scan the process for, well, it will find the executable in the process. It'll check the import address table. If the import address table points to important modules, and these are going to be your kernel 32, NTDLL, WinSock, IP help API. If it points to those modules, it's then going to make sure the pointers are valid, so it doesn't point to the relocation section. It points within where it's supposed to. And it does the same for the export address table. It'll check and again, we have a list of important modules, and we verify that the export address table is pointing in the code section, and it's not pointing in the relocation section. Some people try to do that, and it's not pointing outside the module. So those are things we try to do with the export address table. Kernel hooks, this is much more important, and it's something that is an everyday problem, especially seeing it in spyware now. First, we verify the KE system service descriptor table, which we'll refer to as the SSDT, or the KI service table. It verifies the function pointers, making sure all the function pointers point within the module it's supposed to. We know all the function pointers for no reason whatsoever. They have to point within NTOS kernel. Once we verify they're all pointing within NTOS kernel, we take it a step further, and we load NTOS kernel off of disk. We calculate where the KI service table is in the file locally using a 90210's method, which is pretty good because Kaspersky actually randomizes where it is. And then we just do instruction comparison to make sure the first 12 to 30 bytes, it depends on what we're doing, are the same. So after you get deep enough in a function, you're not going to be able to change the instructions because you're going to throw off the program enough where it won't know what's going on. So you're going to see inline hooks within the first 20 instructions or so. We also check the IDT. We make sure that all the IDT handlers, like your page fault handler, things like that, all point within NTOS kernel. We also then check the actual function handler itself, and we make sure that the function handler doesn't have a known inline hook. This is a Band-Aid. I'm going to actually look into verifying it byte by byte or instruction by instruction, but right now we just do a check, and we do a signature check, essentially, on the preamble. And we also check the system enter MSR to make sure it points to the NTOS kernel. It's a pretty easy check. And finally, we have a list of important drivers so we don't waste our time looking for hooks, and you'll see how fast we actually are able to scan the system. We'll make sure all the ERPs are legitimate. So that's the kernel analysis mode. All right, so those of you who have seen Joanna's talk about DeepDoor, which was, like I said, everything's evolving, so she's got a new thing that hides TCP connections, and we're just picking up the DeepDoor detection. So we are able to analyze and find DeepDoor and UAY-like hooks. And essentially, this is low-level NDIS hooks, which allow the complete stealth command of control channels. So you can essentially hide, with it, you have your own TCP IP stack, and you can bypass the Windows existing one, and you can hide your own ports. You can attach to ports that are owned by other processes. You can do a lot of different things with this. And we know Alexander, I can't pronounce his last name, I do apologize, but the talk after Greg's, before Joanna's, that one is going to cover a lot of this, so that one should be interesting, and he's talking about how to bypass firewalls and stuff. All right, so process detection. We're pretty good at process hiding, so can we be that good at detection? Well, we sat down and we thought about what do we want to do with process detection and what are the problems with the current process detection mechanisms. The major one is they're relying on structures that can be modified quite easily. So what's the common thing that all processes have to have? A process has to have a thread, and it has to have an eProcess structure and an eThread structure. With that, we came up with the idea of signature, creating a signature for those structures. And this signature had to be so that it couldn't be zeroed out. Essentially, if you find our signature, which we're actually going to tell you, so it's not that hard to know what our signature is, you can't null it out so that we won't pick it up. The signature has to be unique. It can't be all over memory, and that also pertains to the signature. It can't have too many false positives, if any. So the signature we came up with, which is pretty good, I say pretty, it's decent. The service table pointer. Every thread has to have a pointer to the service table. If you zeroed it out, you will crash the thread and the process. The service table can either point, depending on the thread, if it's GUI or not, will either point to the KE service descriptor table shadow or the KE service descriptor table. We locate pointers to either one, and then we know that that's a thread, and we look back, find its process, and we keep what we call a master list in the kernel of all the processes we can see in memory. And then what we do is we spawn a process, as we said earlier, with a random name. It looks exactly like you double-clicked on it. It generates a process list that's visible to the user. It's essentially a snapshot if you picture Task Manager being sent to the kernel. So if the process is visible, then we just diff the two lists. Anything that's not in one that's in the other is considered hidden and is reported to the user. And we'll talk about the actual identification of the method they're using and stuff. All right, now this is a really unique feature, and virus analysts and stuff are going to like this a lot. We have the ability to dump processes. This will allow security analysts to take a hidden process or a hooking module, dump it to disk. Even if the file is hidden on disk, we dump it, rename it, and we put it in a different directory. So those are the ways we do it. It's also important to note, and Metasploit has done this, is that you don't need to touch the hard drive to load a hooking module. You can just load it right up into memory and execute it. So keep that in mind when you're dealing with those kinds of things. So as I said, we allow the forensic analysis of hooking modules. You can, if the hook is found in kernel and the hooking module is identified, we give you the option of dumping it. However, as you can see at the bottom, this feature is in beta, and you'll see during the demo, it doesn't work to its correct potential. It always finds the executable module, but we want to be able to dump the actual DLLs in the address space as well. So we're still working that out. It will not be included in the public release this week, but it will be included later. We're not holding it because we want to sell it. We're holding it because it doesn't work correctly right now, or fully. All right, so identification. Once you've analyzed the system and you found all these different types of hooks, you have to identify what kind of hook it is. RAID identifies a ton of hooks. You've got your SSDT overwrite inline hooks, IAT overwrite inline hooks, your EAT overwrite inline and forward hooks, your ERP hooks, your IDT hooks, your MSR hooks, and then open block and characteristic protocol hooks, which are going to be your deep door-like zone alarm hooks. And we also offer the user the ability to identify the type of hidden process. So if we recognize the method being used to hide the process, we'll report to the user, and based on that event, we can then decide, we can give the user a selection of what they want to do with that hidden process. So the two types we recognize are DCOM and PSP-CID table modification, and we'll talk about that in a second. So we had to come up with the list of what methods we want to identify. The two major ones are obviously FU and FU2. They're most prolific. FU is the most widespread rootkit. FU2 is not stable enough with some of the more advanced features to be bundled in spyware, which is an achievement in itself. So if the process is visible by walking the active process links, or is not visible by walking the active process links, it's therefore hidden with DCOM. Automatically we know that. However, we then check the PSP-CID table. If the process is not in the PSP-CID table, it's hidden with FU2, since FU2 combines FU and the PSP-CID table. If it is in the PSP-CID table, we know it's using FU method, and we can then mark it and report to the user what type of method it's using, and you'll see that in the demo, hopefully. All right, so I don't know how many of you were here earlier this morning when they talked about, I don't remember the term they used, but it was, firewalls now act exactly like rootkits. They're going to hook low level, they're going to do deep door hooks. So how do we know what is good and what is bad? And the behavioral analysis was one of the first ideas that came up, and it's been in academia all over the place. And the problem with it, and I've seen rootkit detection tools based on it, is a rootkit will just mimic the behavior of a firewall and bypass it completely. And so it's really, I felt it was a moot point to try behavioral analysis. So what I did was, and this, the problem with this is that every time a driver gets updated, you have to come up with a new signature. But the signature is based on 4 values. You have to have a matching point on all 4. It's almost like a fingerprint. You got to have 5 or 6 point match. Same thing with the driver. We have to be able to match each point. Once it's a match, we know that this driver is installed by this product. We report to the user, and this is good for everyone's mom. It'll say, this hook is installed by this product. Do you have this product installed on your system? If you do, you just type ignore. They will ignore the hooks, and you won't have the option to damage your system by restoring the hooks that were installed there by a product you legitimately installed. So currently, we support the following firewalls. As you can see, it's a list of them. Quick note, Outpost, I don't know if any of you use it. They are using userland hooks. I was a little shocked. So if anyone from Outpost here, come and talk to me. I'll give you code. But yeah, so that was a surprise. But it identifies about 253 hooks installed by all these products, and I'll keep adding as I have time. I've toyed with the idea of putting in a feature into RAID, which will actually dump the signature, and then you can send me the text file and I'll add it in. I'm afraid someone's going to get creative and convince me that this is a firewall and really it's the rootkit, and then I whitelist the rootkit. So I'm a little apprehensive, and it won't be in the public version for sure until I decide. All right, rootkit elimination. We've analyzed the system. We've identified you've got some firewalls, you've got some rootkits. Things are going whack for you. What can we do for you? Well, we offer a couple elimination options. You can restore the original values of the inline hook. So if there's a jump written in memory, we'll overwrite the jump with the actual bytes that are supposed to be there. I think this was called, what was it called? Semantic, the byte-by-byte comparison? In the earlier talk, they had their own term. I can't keep track. Everyone makes up their own terms. So semantic verification, we do it as well. Woohoo. So we're able to restore it using the same method. We also restore the function pointers in the SSDT. And finally, we restore the EAT. So if a driver had his export address table modified, which you see in a lot of, which you're seeing more now, and you also see in a lot of firewalls, we can restore that as well. We also offer some unique restore options for processes. The funniest one is actually decom in reverse. The idea that you unlinked it, but what's stopping me from relinking it back up? So we'll probably show you that as well. It just puts it back in Task Manager. It appears right back after it disappeared. It's nice. You can also close the process if you don't even want to bother to relink it. Doesn't matter either way. With FU2, the process, the operating system is so unaware of the process on the system that doing anything to it is not good, and we don't offer anything just for everyone else's own benefit. So that sort of wraps up the talking portion. And we're now going to, this is a demo. There's at least 6 rootkits, but there's more than 6 hooks. I think there's about 15 hooks, not including the deep door hooks. And the song says it's 10% luck. For those of you who develop on VMware, you'll know that VMware and rootkits and things like that, it's a crapshoot. It's been good all week. I make no promises. I've got a backup, so we're just going to do this. As you can see, there are also going to be 2 hidden processes, WinDBG, RAID, all on VMware, and I'm going to break in WinDBG to show you the hooks, so there's no black magic, nothing up my sleeves. So let's do this. Can you guys, what's the? All right, so we're going to spawn. We got to go full screen. I'm going to enter full screen. Is that better? Yes? All right.